All right. Um, so, um, as for those of you who are right here in the room with me, I'll be able to hang around. I don't know if you have. I know there's a class in this room during the next hour, but I can hang around after class for any questions that don't come up during class. And I'll be sure to make at least a couple more appearances here before the semester is over. Um, okay. Now, as far as announcements are concerned, so what I'm actually going to do, because so I mentioned putting out the free quarter take-home exam on Sunday. I'm actually I'm going to be flying very early in the morning on Sunday, so in order to um, not be affected by any unexpected delays, um, I'm actually going to put it out there the night before. Okay, because I'm not sure what will be going on Sunday. Um, okay, so
So we have an option on that, right?
yes. So to recap, yes, it's been a while since I brought that up. Whoops. Okay. Um, okay. So if you do it, um, homework are 5% each. Exam is 30%. If you don't, homeworks are 12.5% each. And speaking of homework, um, okay, grading on homework 2 underway. Hope to email you with results. I'm going to try to do this like within a few days, like by the end of the weekend. So that way, as the take home is coming out, you have a better idea than you currently do as to where you stand. I've only looked at a few of the homework 2 so far. Actually, generally, they're looking pretty good. So your odds are you're in good shape unless there were, and this is something you would be aware of already, unless there were like multiple problems in homework 2 that you simply did not do. I'm always giving partial credit on these things. The explorations for this assignment, the way I'm doing this is the concept check questions are worth 1 point each, the explorations 2 points each, and then the exercises 3 points each. And where that doesn't um, add up like exactly to 100 or anything, then you get some points for free. So if you didn't do all of them, that gives you an idea of deductions right then and there. Okay, but like I said, I'll be sending emails as I once I get all these done, so you know like where you lost points, just like I did with homework 1. Okay, now so what's on tap for today? That we've been spending a lot of time, and I'm going to take questions on homework 3 in just a little bit. So we've been spending a lot of time on that, just approximating functions of any kind by polynomials because of how easy they are to work with. And what we just did was oscillatory interpolation, particularly Hermite. So approximating f of x using both function and derivative values, and then using divided differences for that. And now what we're doing is actually using these polynomial approximations to approximate derivatives. First, we'll spend most of the time first derivative, but also second, etc. At a given point. So the idea is it's easier for a computer than what you do in your calculus class or other classes where calculus is used. So what do you do when you're working these derivatives out by hand is symbolic differentiation. So that's something that comes nice and easy for us once we learn the rules. But and there's lots of software packages out there that perform symbolic differentiation. It's not playing to a computer's core strengths, which is arithmetic. So that's why numerical is better when the computer is doing all the work. So I'm going to recap this section, talk about the explorations for numerical differentiation that are part of the next assignment. That's homework 4, the final homework. And then where this is going is that we're also going to be using polynomial approximation for definite integrals. So it's the same principle. So you approximate your f of x, whatever it is, by polynomial, and then either differentiate or integrate the polynomial exactly. And a way to think about this, to really sum up what's happening, a theme of this chapter that we're getting into, chapter 8, is the approximation of the exact derivative or integral, same thing, same idea for both, is the exact derivative or integral of the approximation. And polynomials, of course, natural choice because those are the easiest functions to integrate or differentiate. And the thing is, where we end up, once we know how to evaluate or approximate derivatives and integrals, the semester is over. And I'm sure that'll become a big relief to all of you. But then, those of you who go into numerical 2, and I know at least some of you are, then we make use of these for differential equations in 461. Or anytime you want to do anything with continuous functions where you only have discrete data. Like for example, like some more advanced data fitting problems, which we don't get into here. So for instance, if you're given discrete data, for example, daily temperature, then we fit data with continuous functions like polynomials to for the purpose of analysis, because often any analysis of this kind of data relies on calculus. And we can't do that on discrete data directly, so that's why we use polynomial approximation. Also, if any of you are familiar with other kinds of data fitting, like least squares lines that may have come up in certain science courses, like it came up when I took physics. Similar idea that we're using continuous functions to model discrete data. In fact, a statistics professor I knew from Stanford used this kind of analysis to debunk the anecdote that when there was a blackout in New York City in the 1970s, and then what people were saying and repeating to each other was that there were a lot of babies being born 9 months after the blackout. And so this professor harassed the city to gather data on births and study patterns, and found out that really there wasn't. So that's an example of this kind of analysis. Okay. Now, let's see. Okay. That's strange. I have this new page thing that I'm not getting for some reason. Okay, whatever. Now, are there any questions on any part of homework 3 on interpolation? Now's the
I
time.
have a question about the quizzes. Is there going to be a quiz on the last section?
Oh, yes, there will be. I just haven't put it up yet.
Okay.
Yeah, I started to get some submissions on 6.4. And okay, so and that quiz is going to be due actually Saturday, November 4th. So I can put the last one up tonight. But of course, you could also you can see the questions at least. The questions are in the text, so you know what's coming. But yeah, I need to put that into Canvas.
Okay.
All right. All right. So any questions from up there or down here or over there? 614. Okay. Um, okay. So I imagine that it's about the degree 2 case. Um,
I don't even know how I really got the first part of it. I don't, because that's not a system of equations. It's supposed to be a polynomial, right?
oh, okay. Well, actually, it is a system of equations that you're dealing with, and the unknowns in the system of equations, the a0 and a1, so those are the coefficients. Um, Now, one thing I want to make clear about the coefficients is now when you worked this problem, the coefficients for in this case were just for like slope intercept form. Here they're not. Um, so, but the idea is you're expressing p1 as a linear combination of these degree 1 polynomials, and these are the coefficients in that form. So what your matrix looks like um, is so in this case you get a system of equations that you solve for a0 and a1. That's really what you're producing. Now is that something you already had for the degree 1 case? Okay. Now if we take a look at so really the idea is to contrast with 611 because the matrix for this case, you have two entries equal to 1, and you have two entries equal to like an entry equal to x naught, and everyone equal to x1. The point is, in this case, you have a 2 by 2 matrix. None of the entries are 0. But what happened in this one? Yeah, 2 entries were equal to 0, and as a result, because of which entries were 0 and which were non-zero, if you were to go ahead and solve that system of equations for a0 and a1, you'd find it very easy to do. You don't have to do any elimination or substitution. You just divide. So it works out very nicely. That's because the thing is, as far as representing a polynomial, this is how we usually do it. This is often most convenient, but for solving for coefficients, it's actually not. This seemingly inconvenient form works out a lot better for purpose of getting a0 and a1. And in fact, this goes to the contrast between when you are representing your interpolating polynomial in power form. And actually, I'm going to make a comment to this effect here in the notes. Okay. All right, so this is really about, well, we're in section 6.1. So contrast, where'd it go? Where's my text? Okay. Power form and Lagrange form. So in power form, you have an easy basis of polynomials because it's just the monomials. 1x, x squared, etc. But coefficients, difficult to get. Now, in 6.1, you have a system of two equations, two unknowns, no big deal. But now imagine if that system was much larger, much higher degree. Then you're having to expend a lot of effort, whether on paper or by computer, just to solve it. But in a Lagrange form, it's a less convenient basis because it's the Lagrange polynomials. but coefficients are trivial to get. So that's the trade-off in these cases. And what we'll actually see in chapter 8 is how convenient the Lagrange form is because the coefficients are the coefficients literally are the y values. So okay, so you got the correct matrix for the linear case, and a reason. So now to make that leap from degree 1 to degree 2, which I assume is where we're trying to get to now, you want to achieve the same effect where, okay, so for, okay, so to get a similarly simple matrix for the quadratic case, what you want is only one non-zero entry in each row of the matrix, which is what happened in the linear case. You only had 2 entries to begin with, and one of them ended up being 0. So in other words, 1 0 entry, 2 non-zero entries. So this requires you to examine what happened in the linear case to make things work out as nicely as they did. And how to achieve the same in the quadratic case. Now, the thing that will help you do this is extra flexibility. You have 3 points to work with. So x0, x1, x2. And, okay, I can...
Those like contradict each other because you said only one non-zero entry in each row, and you said 1 0 entry.
Hold on, let me make sure I put up my thoughts correctly here. Okay. Oh, yeah, that I had that backwards. One non-zero entry. Yeah. Whoops. Okay, and three coefficients. A0, A1, A2. So the thing is, what happened in the linear case if you're trying to make 2 of the entries equal to 0 in a given row? If you only had first-degree polynomials to work with, you wouldn't be able to make that happen. But with quadratic, you can, because how many roots can it? Because a quadratic polynomial can have 2 roots, and that's something that you can exploit here. All right. So how do you force a quadratic polynomial to have two given roots? And we've seen this before. By working with a factored form of it. Okay. So your so how the equation looks in a general form is, and this was stated in the problem, but I want to expand on it a little bit more. So P2 of xi is equal to yi for I equal to 0, 1, and 2. So you got 3 equations. They all have this form. So if I make it a little more, just a little bit more specific, so by imposing a structure, oh wait, I actually want to number these a little differently. 0, 1, and 2. Okay, so you're going to have three equations. They all have this form. So the matrix entries are so the ij entry. I'll do it this way. Like if P is your matrix, your ij entry is equal to phi j of xi. And I and j are both equal to 0, 0, 1, 2. Okay. And the thing is, it's these polynomials. These are quadratic polynomials, or at least degree at most 2. So you can choose these to have whatever roots you want. So for instance, if you're plugging in, let's say you're plugging in x0, and you want to make 2 of these polynomials vanish at x0, then you're taking advantage of its expressing in factored form will do that. Okay. Okay, so see if you can work with that to figure out how to choose these so that you have the same kind of nice, simple system of equations in the end. And seeing what happened in degree 1 and then what happened in degree 2, then this is not part of the problem, but you would see how this would generalize to any degree. All right, so any further homework-free questions? Okay, well, if you think of any, we still have 50 minutes for any to come up. All right. Now, okay, I want to point out that, okay, make this a little bigger. Okay, since I'm talking about the numerical differentiation section today, I've started rolling out homework 4. So just by picking out the explorations and concept check questions. Now this is something else I'll put in Canvas. As you can see, not due for a while because we have other things coming up, like the completion of homework 3, the take home for those of you who choose to do that. And here we have the recommended deadlines for each of these sections. I'm not assigning any of the exercises at the end of a chapter, like I have here, just because we ran out of semester. So by the time if I give you enough time for these sections, take into account Thanksgiving break, there's a gap in here, that things got a little too crammed. But I'll be assigning in roughly this number of explorations from each of these sections, and so pretty soon I'll be choosing the rest of these. Okay. All right. So what I'm going to do is review the essentials for numerical differentiation, and then I'm going to talk about these 4 explorations. Gives you some tips on those. So one thing I want to remind you of, and this certainly applies for homework 3 also, that you have in progress, that if you look at the schedule, the classes that we've had lately, as you move through the different sections on homework 3, these last several classes, these are the ones you'll want, the videos you want to refer back to as you're going. So, for instance, as you get to section, say, 6.3 on Newton interpolation, you'll want to look at this video and the notes that I put out for the tips on the explorations for that section. Okay. And similarly, once you get to homework 4, you want to refer back to today. Okay. But I'll include everything in the notes so that you're not having to go back and watch the video. Okay. So with numerical differentiation. So the problem. Actually, let's start a new page with this. Okay. All right. So the problem we're considering in this section is given function f of x and some point x naught, approximate f prime of x naught, mostly interested in first derivative, or higher order derivatives, f double prime, f triple prime, etc. And we have two approaches to solving this problem. Okay, so for first one, and you've got a taste of this already from homework 2, and that is Taylor expansion. So the idea is your approximate. Now I'm going to use a first derivative here for convenience, but similar things will apply to higher order derivatives. So your approximation is okay. So you have 1 over h out front. So we have a spacing h, and this form is in the text, but I'll reproduce it here. So the idea is you have a spacing h. So we have points that are equally spaced. Equally spaced points is not required, but it is used so often that's what we're going to stick with in our discussion here. So you have points on either side of x naught that you're using. That's why I have indices that are allowed to be either positive or negative. And what you do is you evaluate your function at those points, and then what you're doing is you're trying to find the magic way to combine those values to approximate the derivative at that point, or whatever derivative that you want. So what you do is, to get the coefficients, which I should mention are independent of f itself, they're also independent of x naught. So really they only depend on the locations of these points that you're using relative to x naught. So for instance, if I'm using x naught plus h and x naught plus 2h, so points only to the right, we're assuming h is positive here, it will get a very different set of coefficients than if I use like 1 point on the left or 1 point on the right. So what we do is we Taylor expand all of these other values. And we always use a center x naught. So then what you do is you take linear combinations of these expansions, and the coefficients are these c's that we're trying to get. So these are unknowns at this point. And what you get is a system of linear equations. And I'm going to refer you to example 811, where this is actually worked out. I'll show you. Okay. Oh, not 811. It's okay, 812. All right, so here I'm using 3 points, x naught plus h, x naught plus 2h, to approximate the first derivative. And I'm going to have some error. And in fact, I should have put that here in the notes. F prime is not exactly equal to that. We wish. Okay. So we have some error that we also want to estimate. Okay. And what happens is I have 2 values, x naught plus h, x naught plus 2h, f at both of those points. I need to Taylor expand them. And so now if I take c naught times f of x naught plus c1 times this plus c2 times this. So in other words, I'm taking these expansions and substituting them into my form. Here's the form of my approximation up here. So once I do that, I want to get out of this f prime of x naught. So I get this system of 3 equations in the free unknowns because I want the f terms to cancel. I want the f prime terms to combine to give me just f prime of x naught by itself. That's why I have this 1 right here. I want the second derivative terms to cancel. Now, after that, I have no more flexibility. I'm not going to be able to get these terms to cancel. That's where the error is going to come from. So now I have a system of equations. This is something you solve like using Gaussian elimination, like you did it in, like for instance, Math 326, or you can have MATLAB do it for you, which I'll show you in a bit. Here are your coefficients, and now you have your approximation. And you can also, now that you know how to combine these Taylor expansions to get the first derivative, you can also use that to get the error. So, so here we have some estimate of the error. And the important thing to keep in mind here is, in this formula, the error is order h squared. It's that power of h that we're particularly interested in. So we have some formulas that are first order accurate. The error is proportional to h. We certainly prefer formulas with the error proportional to h squared, or a higher power of h is even better. So this is one of the approaches using these Taylor expansions and figuring out how to combine them linearly to get the derivative you want to fall out of that, and then as many of her terms as you can cancel. Okay. Now the second approach is using Lagrange interpolation. So we fit f of x at these points, x naught plus I. So same points you're using, same indices, to get a polynomial, interpolating polynomial, which I always refer to as Pn of x, where in this case n is equal to j plus k. Because if you look at all the indices from minus j to k, and that would give you n plus 1 points. And as we know from interpolation, you have n plus 1 points, it gives you a polynomial of degree n. And you express in Lagrange form. So Lagrange form would be the sum of your function values times the Lagrange polynomials of degree n, and I'm using I as an index. So this is just straight Lagrange interpolation, no different than what happens in chapter 6. And then you differentiate that exactly, because that's a polynomial. So you get the Pn prime and x naught. Okay, so in other words, the derivative you really want, f prime of x naught, is approximately derivative of this polynomial, and that would be, okay, so I'll go ahead and copy this. But now what's happening is I'm differentiating the Lagrange polynomials and plugging in x naught into the derivatives. So now, I need to zoom out a little bit. If I compare this form of the approximation with this one right here, it turns out that that's where we get the coefficients. So Ci over h is equal to Lagrange polynomial prime at x naught. So differentiating Lagrange polynomials, plugging in x naught, gives us the coefficients. And the coefficients will be the same using either approach, because really both approaches are using polynomial interpolation, because what are we using here with Taylor expansion? If you we think of it, we often call this Taylor series, but if we take a Taylor series and we cut it off at a certain point, that's not a Taylor series. What is that? What do we call that? So if like a Taylor series is cut off after a finite number of terms, it's a Taylor polynomial, and then you have a remainder term from which you get the error. So we're using polynomial approximation in both cases. That's why the coefficients we get are the same. So you could use either approach to approximate a derivative, but for a first derivative especially, Lagrange approach is better for getting the error formula. Because in fact, in the example that I just showed you, example 812, we don't get the error formula completely. We like to have it as a single term, but using Lagrange, you can. But for higher order derivatives, it gets a little dicier for both. Okay. So any questions about the two approaches for approximating derivatives? Okay. So what you'll be doing in the explorations is making use of both approaches. And so I'm going to take some time to now here, like I said, I'm assuming first derivative. Second derivative, not much difference. Like for instance, in the Taylor expansion case, you want the first derivative terms to cancel if it's second derivative or after, and then you want the coefficients of second derivative to add up to 1. If it's Lagrange, if I want second derivative, I would just take the second derivative of the Lagrange polynomials and then plug in x naught. So there's so once you have first derivative figured out, then second derivative isn't really an issue after that. So I'm going to take some time to talk about the explorations for this section. Okay, and I assigned, make sure I get the numbers right, 1, 4, 5, and 6. Yeah, 1, 4, 5, and 6. Okay. Now, so let's take a look at these. Whoops. Okay. So in the first one, what you're doing is so I'm pointing you to the example, and that's what I'm going to try to do in each of these problems. If there's a specific example or a specific equation, so I don't want you sifting through the whole section to find out what you need. So modeling this example using Taylor series, but now using more points. Instead of using f of x naught and then x naught plus h and x naught plus 2h, using x naught plus or minus h and then x naught plus or minus 2h. So that's what I mean by for j equals 1 to 2. So there's 4 points altogether to get a approximation of f prime again, but this time it's going to be higher order accurate, because the larger number of points is going to give you more flexibility, which allows you to get more terms in your Taylor expansions to cancel. So what you're going to get is okay. so you get a system of 4 equations, 4 unknowns, for coefficients of f of x naught plus or minus h, and f of x naught plus or minus 2h. One thing to keep in mind is you're going to naturally benefit from symmetry. You have 2 points on the left of x naught, 2 points on the right. So normally 4 points would only give you a third order accurate approximation, but because they're symmetric, you're going to get 1 more degree for free. That's why it's going to turn out to be 4th order. Okay. And the thing is, what you could do is you can either, I don't really care if you solve this system on paper or if you have MATLAB do it, that's fine. In fact, I'm going to mention something that can help you with that. Let's see. Okay. So you set up a similar system to, like I said, example 812. Now, the next exploration, 812, I did not assign this one, but it plays a role in a later one that I did assign, and that's why I've actually gone to the steps of working out this one for you. So I've posted some code on the site under today's entry, November 2nd, makediffrule.m. So this is a function for exploration 812, and I have it up here. So what this does is, so I figured you could use this coding example anyway, since I have you do lots of functions. So anytime I assign you a function, I'm always specifying what are the inputs and what are the outputs. And I want the first line of your M file to be literally this, function and then outputs equals input, just for the sake of uniformity. So that's what I have here. This function, c equals makediffrule p. P is a vector of inputs. And so what's done here is n is the degree of a polynomial approximation that I'm using. So I'm going to have a system of n plus 1 equations, n plus 1 unknowns for whatever n is. The right-hand side, if you look at the example that this is based on, this example here, notice all the right-hand side values are 0, except for the second one. And the reason why is, in a Taylor expansion, the second term is your first derivative. So that's what I put here. I make a vector of all zeros, a column vector. I set the second element equal to 1. So it mimics what's going on in the example here. And then I need to fill in my matrix. So for my matrix, what I'm doing is the vector p holds all my spacings. For instance, if I'm using the points x naught and x naught plus h and x naught plus 2h, my spacings would be 0, 1, and 2. So I take those multiples of h, what I'm doing here is I'm actually assuming h equals 1, because then I'm just going to get the coefficients and divide by h afterwards. And I raise them to a power. Which power? It depends on what row I'm in. Because look at the system of equations in the example. The matrix entries for first row, they're all 1s. For all my spacings raised to the 0 power, which would be 1. In the second row, it's all the spacings, h and 2h, raised to the first power. And then I have the spacings raised to the second power divided by that factorial, although we're set equal to 0, so I actually don't need the factorial. In fact, that's why I don't have it in here. It's not absolutely necessary. So raising your spacings to higher and higher powers, so 0 power, first power, second power, and so on, gives you the entries in your coefficients of your system of linear equations. So these two loops fill in those coefficients. And now I solve a system. But in MATLAB, it's very easy. You just use a backslash operator. So C is a solution of a system of linear equations. A times C is equal to B. So now I'm going to use this to show you the usage here. Okay, so if I do make diff rule, and I give a spacing of 0, 1, and 2. So this corresponds to x naught plus h, x naught plus 2h. Okay, and the output will be vector c. Oh, sorry. I was doing stuff with floating point arithmetic earlier, part of grading homework 2, so I had format hex going. Not very helpful here. Okay, so what are my coefficients? Minus 3/2, 2, and minus 1/2. Now, if I chose this one because that's the same as in the example in the book. So if I flip back to that, over here are my coefficients. Minus 3/2 over h, 2 over h, and then minus 1/2 over h. So basically you have a function that works out the coefficients for you, at least for first derivative. So this handles first derivative, but you'd have to tweak it if you wanted higher order derivatives. Okay. Now, what I want to make clear about this exploration 811 here is okay. I want to take a look at some of the other rules that I have in here. Okay. Now, must use Taylor expansion, as in work it out. Now one thing you don't have to solve the system of equations by hand, but do have to set it up that way. And so for instance, if you figure out the system of equations, if you want, you can put that into MATLAB and have it solve it. I don't care about that because that's a 326 thing. But to check answers, well, the differentiation rule is actually worked out. It's right here. So you see what you're supposed to get. I just want you to show me that you understand the process. So it's the 5-point formula that's on page 283. Okay, and it's okay. That uses and we see it's 4/4 accurate. The error is proportional to h to the 4th. Okay. All right. So you can see what you're supposed to get anyway. All right. So let's make sure clear what the rules are on that problem. Okay. So questions about what to do with this one. Okay. So follow the example, and it should work out for you. Okay, the remaining problems in this section actually deal with the Lagrange approach. So what's happening in Lagrange is this part is what I showed you earlier. That's already in the notes. So my f prime is equal to this part. This part that I'm highlighting, that's the approximation. So you've seen that already. Everything else, this is the error. So the task in exploration 814 is to basically simplify this. Because what I'm doing here is, in this formula, I'm not making any assumptions about what the points xi are. I'm not requiring that they're equally spaced. But But in this problem, you do. So so basically fill in the assumption that xi is equal to x naught plus ih, where I is equal to minus j, and so forth, up to k. And so once you fill this in, you want the goal is to simplify as much as possible, because then you get a nice compact expression for the error that does not require a product. You're basically going to get a single number in terms of j and k, because the error should be of a form like higher order derivative, the n plus first derivative at an unknown point over n plus 1 factorial times some constant. So what this problem is about is what's the constant, and so it'll be in terms of j and k. So and what I would suggest is to see, once you fill this in, like to see what the pattern is. Try on a simple example by choosing specific values for, whoops, that should be minus j up to k, not minus k. Okay. Specific values for, dang it, stop that. Okay, this is getting really aggravating. There, for j and k. And like I said in the problem, and compare to error formulas in a section. Because what we have in the page following, we have several examples of these differentiation formulas with the error formulas. So you can figure out, like for instance, in this one right here, j is equal to 0, because we don't have any points to the left of x naught. K is equal to 2. For this one, j is equal to 2, and k is also equal to 2. And then over here, j is equal to 0, and k is equal to 4. So, so if you were to try this out for those kind of values and see, oh, here's the error formula you're supposed to get, then you can see what the pattern is. And then once you substitute in xi is equal to x naught plus ih, you can see there's some simplification here right off the bat. But you want to simplify as much as you can, like what the pattern is. And you might be able to see it more easily if you work with a specific value of j and k. Right. Now, the next problem, 815, you're basically tossing out the make-diff rule function that I provided for Taylor series expansion, and instead using a whole other approach, using Lagrange interpolation. So what you could do is, if you call this function, it'll still spit out the same kind of coefficients. In fact, exactly the same coefficients, but it's using Lagrange interpolation to get them. And also, based on the result of this problem, you can make it compute the error constant. Basically, it's this constant that also gets returned as an output. But once you've worked this one out, you could use whatever formula you get here in here directly. So that there really isn't complexity added by including that in here. But as for how to use Lagrange interpolation, what you need to do is use some of the MATLAB polynomial functions to help you out. So to create Lagrange polynomials, use polyfit with x values coming from the vector of indices p that gets passed in as a input argument, and And then for y values, now, testing your knowledge of Lagrange polynomials. What do we know about the values of Lagrange polynomials? What are they equal to at any specific points? And you just dealt with this in one of the quizzes. So definitely somebody here knows it. Or up there. Don't be shy. What defines Lagrange polynomials? For values at particular points, what are these values?
Interpolation points?
Well, those are the x values, but what are they equal to at those points? Specific numbers.
0?
Yeah, and
1.
yeah, they're equal to 1 at one of the points and 0 at all the others. So the y values would be all 0 except one 1. Now, a convenient way to do this, you have a total of n plus 1 polynomials. In other words, the length of p. So the easy way to get these values is can use the I command to get a n plus 1 by n plus 1 identity matrix. Whoops. Because each column has all zeros except one of the values is equal to 1. So it's a convenient way. If you just take the identity matrix, you take one column at a time, use that as your actually column or row, it doesn't matter. Whatever's more convenient. Actually, perhaps row because we can assume that P is a row vector. In fact, I'll put that in here. Okay. Okay. Whoops. Okay, well, so I'll let you assume that. So I'll just say row. Let's make it a little easier there. Okay, so the rows of the identity matrix give you all of the y values you need. So one row per Lagrange polynomial. So if you have the x values and the y values, and Lagrange polynomials in this case are of degree n, and that's important because stop that. Because polyfit requires three arguments: x values, y values, and the degree. Okay, and then you can use polydir to get the derivative of a polynomial, and also you've used this function before, polyval, to evaluate at a point. Now, in this case, like I said, the coefficients do not depend on x naught or f. They depend on the locations of the points relative to x naught. And so in this case, it's a 0 that you would use because your indices minus j to k, those indicate spacings, multiples of h, away from x naught. Well, at x naught, you're right there, so that would correspond to the point 0. Okay. So be sure to check against known examples. Also should return the same results as my function that I've just posted, because we're generating the same rule, just using different approaches. Okay. So you have plenty of ways to make sure that you did it correctly. Okay. And finally, okay, number 6, a second derivative rule. So using both approaches, based on examples that are already given. Now the examples were for first derivative, but you're modifying it for a second derivative. So so at least via Taylor expansions, also forming Lagrange polynomials. Okay. Now, any linear systems you can solve using MATLAB. I don't care about that. Okay. Also, well, actually, I mentioned polynomial evaluation, but any Lagrange polynomials are evaluated 0. Don't need any computer help or even calculator help with that. Okay. Now, as far as the error formula goes, I would recommend use a Taylor series approach. That will be easier for purpose of getting the error formula. Really, I don't care how you get it, but it's just definitely going to be easier that way. Okay. And of course, you should get the same result in both cases. So differences from the examples. So for Taylor series, different, same matrix, because the points are the same. X naught plus h, x naught plus 2h. Different right-hand side. You want the first derivative terms to cancel. Okay. And then for Lagrange, you just take the second derivative. And x naught, or really 0 that you're using, instead of a first derivative. That's the only difference in that approach. Okay. So hopefully these will put you on the right path when you get to these problems for a purpose of for working these out. Okay. So are there any questions about what's going on with, well, actually we have 9 minutes. So we have time for questions for anything, whether it's what I've just shown you about differentiation or what's going on with homework 3.
Okay, I do have a question for 6.3.8, if I remember correctly. We have to set the I'm basically having issues getting the points to sit into the matrix correctly.
Okay, so is it this problem? Wait.
Yeah.
Okay.
This one before it's 0.3.6.
Oh, 636. Okay.
Yeah, sorry.
Okay, no problem. Okay. Okay, so in other words, implementing this. Okay. All right.
Unless you got for 6-6.
Uh,
3-6.
uh, yeah, but this, problem 636 is, but you're implementing this.
Okay.
Yeah. Okay. So what's happening is, okay. So what is it you're having trouble with?
Um, getting it to write correctly to the getting it to write correctly to the end C basically.
Okay. So it's running all the way to the end, or is it running to the end? You're getting incorrect value.
I can't get it past the first for loop, unfortunately.
Okay, like you're getting an error message.
Yeah.
Okay. Can you tell me what the error message is?
It just says error at line 10. I think it has I think it's having issues with putting in X and Y itself.
Okay. All right. It might be something. Well, okay. If necessary, I can always look at your code later. But okay. So, but what you're telling me is it's not able to do like this first for loop. Something goes wrong while doing this.
Yes.
Okay. Um, so what? Okay. So the first thing, um, are you shifting the I values? That's important.
I'm trying, and I think that's what it's throwing.
Yeah, because now there's nothing wrong with using the same I values, like having I going from 0 to n, but then as soon as you use that I value as an index into a vector, which is what's going on here, like you have this, what you're given is this vector of, these are your vectors of y values that are given. So you'd have to use I plus 1 as, so if you're using I equals 0 to n, just like is written here, you got to use I plus 1 for now in this forming this matrix D. Here, instead of a 0, you'd use 1 for the first column, and then you'd use I plus 1 for the row index. You'd also use I plus 1 as an index into your vector of y values. Yeah. So if you're using exactly the same indices as in the algorithm, that shift is going to be necessary in lots of places. Although what happens is when you have a difference of indices, like right here, the I minus j, those plus ones just end up canceling each other out. So in fact, it's not necessary in that case, but elsewhere, it certainly is. In fact, all three of these statements where you're dealing with indices, that has to be used. So if you continue to have trouble, um, if you're unable to get it working, go ahead and show me your code. Okay. All right. All right. Still have 4 minutes. Any other? All right. Now, what's going to be happening on Tuesday? Whoops, wrong chapter. Okay. Now, what I've been doing after I kind of hit the reset button some weeks ago was go back over chapter 3 and also this first section on numerical differentiation. Tuesday will be the first time in a while that I'm covering something that is completely new to you, getting into numerical integration, which still relies on polynomial interpolation, but now instead of differentiating and plugging in x naught, we're taking the definite integral from a to b. This is what I'm going to be covering. And of course, you can always refer to the schedule 8.2, which starts out with the very basics of numerical integration. So what I would recommend is giving this section a look. I will be going over the essential points of this section on Tuesday, and also any whatever explorations I assign. It's not a very long section; it doesn't go very far. But to better follow what I talk about in class, again, since this is going to be entirely new to you, I'd recommend just taking some time to look over the section before class, just so you're at least partially in the know, and then whatever I cover will make more sense. Okay. So keep an eye out if for those of you wanting to do the take home Saturday night sometime while I'll be in Seattle. To I'm just going to email it as an attachment to everybody, but I'll also post it on the site. Okay. So, all right. So I hope someone up there took attendance. Please send that to me, so I can have all the data. Okay. And for those of you who are taking probability stats 2, good luck on the test that you're about to take. All right.